Earlier, I said that in this lecture, we are going to revisit some of the concepts that we have already talked about, and that start now. Let's say I have a bunch of vectors and I want to know whether they span a square. We have talked about this in lecture 3 in particular. This is going to be in example 3.6. To check whether or not a list of vectors would span R to the m, all I need to do is that I just have to put them into a matrix form. So my matrix A is just a bunch of vectors put together. This is going to be an m by n matrix, where n, this is going to be the number of vectors that I have, and m is going to be the number of coordinates. In this example, because my vectors are all in R squared, they have 2 coordinates, so the value of my m is going to be 2. Now, to check if they are going to span R square, or in general, if they are going to span R to the m, that is going to happen precisely when the rank of my matrix A here is equal to m. And we also knew that if my n is less than m, and that means I do not have enough vectors. If I do not have enough vectors, then I can tell that those vectors are not going to span for sure. They cannot span R to the m for sure. So, if I look at the example down here, now for the first 3 cases, because I want to span R square, then that means if I only have 1 vector, then they are not going to be enough. That's not going to be enough. So these guys cannot span R square for sure. Now, we have done some of these already. If I want to be sure, then I can just find the rank of the matrix that I got by putting this vector together. I'm going to have rank of 1, 0, 0, 1. This is going to be 2. The rank of 1, 0, 2, 3. This is going to be 2 as well. Rank of 2, 3, and 4, 6. 2, 3, and 4, 6. This is going to be 1. The rank of the next one, 1, 0, 0, 1, and 2, 3. This is going to be 2. And the rank of the last one, 1, 0, 2, 0, 3, 0. This is going to be 1. Now then, these guys are going to span R square when the rank is equal to 2. So I can tell then that they are going to span precisely in this case, and in this case. And for the other two, they are not going to span R square. And next, I need to know whether they are linearly independent. And we have talked about this in lecture 4, specifically in example 4.4. We knew that they are going to be linearly independent. They are going to be independent precisely when the rank of the matrix is equal to the number of vectors that I have. So they are going to be independent precisely when the rank of the matrix equal to n, which is the number of vectors. And we also knew from the next example, from example 4.5, that if I have too many vectors, if my n is greater than m, that means I have too many vectors. In that case, my vectors, they are not going to be independent for sure. They will not be independent for sure. Let me actually kind of move this up a little bit. Okay, now I get the R with me. Let me kind of move this down. Okay. So then I can tell that from the bottom 2 cases here, because I have 3 vectors, but they are in R square, so they are not going to be linearly independent for sure. For the first 3 cases, because I only have 1 vector, so there's nothing to be linearly independent about because I only have 1 vector, so these guys are going to be linearly independent for sure. Or if you want to check, you can find that the rank of the matrix that I get by just putting this into a vector form is just going to be 1. And that's the same for the other 2 cases as well. The rank of 0, 1, this is just going to be 1. And the rank of 2, 3, this is just going to be 1. And because the rank is equal to the number of vectors that I have, so they are linearly independent. So for the next one, the rank equal to number of vectors, so they are independent. The rank equal to number of vectors, so they are independent. And then, wait a minute, let me make this green. And for this one because the rank does not equal to the number of vectors, so they are not independent. And now then, for this lecture, we are going to be interested in the case when the list of vectors that I have span the vector space. So in this case, it's going to span R squared and also are linearly independent. So that will correspond to precisely the two cases that I have here. Whenever this happens, whenever my set of vectors span the vector space and they are linearly independent, I'm gonna say that they are a basis for that vector space. And also the dimension of the vector space is just the number of bases that I have. Notice that we usually say that R squared has dimension 2, and that's because if I were to find a basis for that vector space, then the number of vectors I have here is always going to be 2.